Hi guys, welcome back to our discussion on infinite series. So in this video, we will discuss about the ratio and the root test. Okay, before we discuss the definition of the ratio test and example, so let us first define or discuss the objectives of this lesson. So number one, use the ratio test to determine whether a series converge or diverge. Then use the root test to determine whether a given series converge or diverge. And the last one is to review the test for convergence and divergence of an infinite series. Okay, our next test is the ratio test for absolute convergence. So according to this theorem, that summation of b sub a sub n be a series with non-zero terms. So number one, the series summation of a sub n converge absolutely when the limits of the absolute value of the quotient a sub n plus 1 over a sub n as n approaches infinity is less than 1. The number two, the series summation of a sub n diverge when the limits of the absolute value of a sub n plus 1 all over a sub n as n approaches infinity is greater than 1 or equal to infinity. And then last, the ratio test is inconclusive when the limits of the absolute value of the ratio of a sub n plus 1 and a sub n as n approaches infinity is equal to 1. Okay, for example, determine the convergence or divergence of the given series summation of 2 to the n over n factorial as n is from 0 to positive infinity. Okay, so from this given series, now we can define the n term of the series as 2 to the n over n factorial. And then by using the formula, the limits of absolute value of this is a sub n plus 1 over a sub n as n approaches infinity can be written as the limits of a sub n plus 1 where a sub n plus 1 is obtained by replacing all the n variable by n plus 1. So this now can be written as 2 raised to n plus 1 all over n plus 1 factorial divided by a sub n, but a sub n is given as 2 to the n over n factorial. Then we change the division to multiplication, but we have to get the reciprocal of 2 to the n over n factorial, which is n factorial over 2 to the n. Then multiplying these two, since you can write 2 to the n plus 1 as product of 2 to the n and 2. So you can write this as the limits of 2 raised to n times 2 all over. In the denominator, you can write this as n times n plus 1 factorial. Sorry. This should be n plus 1 times n factorial multiplied by n factorial all over 2 to the n. As n approaches positive infinity. And because 2 to the n is common, so you can cancel this out. Same with n factorial. So you can write this as 2 over n plus 1. And to evaluate this, we replace all the n variable by infinity. So you have 2 over infinity plus 1. But you can write this as 2 all over infinity plus 1. But infinity plus 1 is infinity, and 2 over infinity is 0. And because 0 is less than 1, then we can therefore conclude that this series converge absolutely, na because the limits of absolute value of a sub n plus 1 over a sub n is less than 1. Okay, or this series converge because the limits of the absolute value of a sub n plus 1 all over a sub n is less than 1. Okay, so in summary, given the summation of u sub k, a series with positive terms, and suppose that rho is equal to the limits of u sub k plus 1 over u sub k as k approaches positive infinity. So if the value of rho is less than 1, then we can say that this series converge. If it is greater than 1 or positive infinity, then the series diverge. But if rho is equal to 1, then the series may diverge or converge, so that another test must be tried. Or if we use the ratio test for absolute convergence, given the summation of a sub n, we can say that the series converge absolutely when the limits of the absolute value of a sub n plus 1 over a sub n as n approaches infinity is less than 1. Or if this is greater than 1 or infinity, then this series diverge. But if the limits is equal to 1, then the ratio test for absolute convergence is inconclusive.